Welcome to lecture 26 of Introduction to Quantum Field Theory. In this lecture, I will discuss the ON vector model as a quantum field theory. Recall that in lecture 22, we discussed the quantum field theory of a complex scalar field phi. When we were separating phi into a real and an imaginary part, phi1 and phi2 respectively, we found that we could write the quantum field theory partition function in terms of the path integral that's listed in equation 26.1. In this lecture, what I wanted to do is to generalize a two-component scalar field to an n-component field that is denoted as a vector here, as a generalization of the complex scalar field results that we found in lecture 22. Recall that for a single complex scalar field, we had in lecture 22 the result for the Euclidean action that we used in this particular study. We found that this action here had an additional symmetry. It is invariant under the transformation phi going to e to the I alpha times phi and the complex conjugate phi star transforming accordingly with a minus sign in the exponential, where alpha here was an arbitrary parameter with the only requirement that it was constant. This is usually called a U1 transformation because we can think of e to the I alpha as a 1 times 1 matrix, basically just a number, and it is unitary because we have e to the I alpha times its complex conjugate is just 1. When we write the action for that complex scalar field in components phi1 and phi2, the same action becomes the expression that's listed here in equation 26.5. In components then, the U1 symmetry that I just discussed on the previous slide now becomes a transformation for the two components phi1 and phi2 that's given as this matrix here, cosine alpha, sine alpha, minus sine alpha, cosine alpha on these two components, where again alpha is the same constant that we had before. The idea is now that we think of phi1 and phi2, the real and imaginary part of the original complex scalar field, as coordinates of a vector in a two-dimensional plane. With this interpretation, this transformation matrix given in equation 26.6 is then nothing else but the rotation of the vector in this two-dimensional plane. And this rotation matrix is also called an SO2 transformation matrix, SO2 standing for special meaning unit determinant, orthogonal, and 2 standing for a 2 by 2 matrix. Now let us discuss how to set up the ON vector model in that regard. We have talked about the complex scalar field being represented by a vector in a two-dimensional plane, so a two-component vector. And there is an obvious generalization to this setup. We can generalize the two-component vector to a vector with n components, phi1, phi2, and so on to phi n. And we sort of represent this vector in terms of this particular symbol here. In addition to the usual Lorentz invariance, we will expect the action for that ON vector model to be invariant under an SON symmetry as a generalization of the SO2 rotation symmetry that we had for the complex scalar field. In 3+1 dimensions, it's not hard to write down what the form of such an action has to be. Essentially, we can just take the result of the previous slide and replace it by only combinations that are invariant under these rotations in an n-dimensional space. And equation 26.8 is one particular generalization of this action to n components. Now note that this has a particular coupling constant that involves the number of components n. The reason being that if we have particular values of n, such as 1 or 2, we want to get back to the familiar examples of a single real scalar field and a complex scalar field that we discussed before. So in particular, n is 2 will just cancel with the 2 in the numerator and just give us back the usual complex scalar field. The quantum field theory that arises from quantizing this classical action is called the ON vector model. And the partition function for the ON vector model is simply given as the path integral over all components phi vector of the exponent of minus this Euclidean action. As I said before, for two components n is 2, the ON vector model action, and hence the whole quantum field theory, just reduces to the quantum field theory for the complex scalar field. By contrast, for n is 1, the ON vector model reduces to the quantum field theory for a single real scalar field, albeit with double the coupling constant. Let us now talk about how to solve the ON vector model. So far, whenever we had an interacting quantum field theory, we were trying to get an idea of what the quantum field theory was doing by using perturbation theory, basically treating the interaction term as a small perturbation and doing a Taylor expansion of the exponential of this term. In the ON vector model, we have a huge advantage over, for instance, the real scalar field. We are actually able to solve the theory exactly in the large n limit. This is a rare case when one does not need perturbation theory in order to understand a quantum field theory. I will be covering the basics here, but clearly this study of the ON vector model is a very rich subject. And if there is interest from in particular advanced students, I'll refer to a recent reference that you can just click on here. Now, to solve the ON vector model in the large n limit, we do a couple of tricks that I'll go through in the next few slides. We first insert unity in the path integral for the partition function. So we have our path integral and we just write in unity. Next, we write the unity in terms of an integration over delta function. The only maybe non-traditional way to do this is to write it as a path integral over delta function. So really we're inserting an infinite number of integrals over an infinite number of delta functions. Once we do that, we can use the delta function in order to replace the quartic term in the action by sigma squared, because the delta function says that whenever we have phi dot phi, we can replace it by sigma. And going back to the action, here we can replace this term here just by sigma squared. Once we have done that, we can write the delta function in terms of an integral representation. Again, this is a functional integral, so we have a path integral over d zeta, which is a new auxiliary field, times e to the I integral over zeta times the argument of the delta function. Doing these steps, we get a new path integral representation for the partition function z. It's a path integral over the original ON vector field phi, and path integral over the first auxiliary field sigma, and a path integral over the second auxiliary field zeta. And then we have an action here, which has the advantage that is quadratic, both in the auxiliary field sigma, as well as in the original field phi vector. In particular, since the path integral over the auxiliary field sigma here is Gaussian, we can just integrate out the field sigma here by usual Gaussian integration and get a path integral that only involves now the original field phi vector and the auxiliary field zeta. In particular, if we now rescale zeta to n times zeta, we find the following representation for the path integral. It's given in this equation 26.15 here. In principle, this sort of result here is quadratic. The only problem being that both zeta and phi can depend on space. So this term here in this part of the action is basically a 3-point vertex and leads to an integration that we cannot treat exactly because it's not Gaussian. It's a 3-point function here. However, what we can do is we can first separate the auxiliary field zeta in terms of a mean field, a constant component zeta bar, and fluctuations around that, just as we have done in lecture 19 when we were talking about spontaneous symmetry breaking of the scalar field. If we do this, we plug it in, we find that since the fluctuation part clearly integrates to 0, there's no linear term in this expansion of the original quadratic term up here. So this is the action that we get. And I just wanted to point out that up to this point here, everything was still completely exact for any n. So we could put in n is 1, and this path integral here would basically represent the single real scalar field theory that we've talked about quite a bit in this course. However, what we can do now is we can use the large n limit to get an exact result for this particular ON model B theory. The first trick, is to realize that for large n, the path integral over the fluctuations gives a contribution that is, let me back up here. If we integrate over the path integral over the fluctuations, we have something that sort of scales with n times sigma prime. So while it's complicated to integrate out that piece exactly, we'll get something that is basically involving this n here only as a factor. So we'll get that down in the so not up in the exponent, but down in the usual integrand here. So what that means is we get something that is order n. Order n is the same as e to the log n. That's the contribution from the integration over sigma prime. However, the mean field term itself has an n in front. So basically we get e to the n from the mean field term, but only e to the log n for the integral over the fluctuations sigma prime. So what that means is that in the large n limit, e to the n is much, much bigger than e to the log n, and we can neglect e to the log n contributions with respect to the leading order mean field term here. So this greatly simplifies the discussion because it means that we can neglect the path integral over the fluctuations, and we only get an integral that involves now the usual integral over the mean field and the path integral over the ON vector field. The remaining path integral over the ON vector field is now again Gaussian because this term, which was previously a 3-point function, now is just something like a generalized mass term because sigma bar is constant. And we can just integrate that and get the determinant of this operator. The determinant of this operator is something that we've calculated before. This is nothing else but the partition function of a free scalar field with a particular mass term. And we get that in the large n limit, the partition function is just given as the integral over the mean field, e to the n, because we have n copies of this operator here, the logarithm of the free partition function for a real scalar field, with an unusual mass term that is the square root of the usual of the mass in the Lagrangian plus essentially this mean field term in here. The remaining integral over the mean field can be evaluated using the saddle point approximation. And since again we are in the large n limit, the saddle point approximation is not actually an approximation, it is exact because all the sort of higher order contributions are subdominant in the large n limit. So if we denote the position of this saddle as sigma zeta tilde, we find that the result for the partition function in the large n limit is given by this expression here. It's e to the n, the logarithm of the free partition function of a single scalar, minus a term that also involves the value of the position of the saddle. We can use thermodynamic relations, such as this one, to rewrite this result for the partition function as e to the n beta v, where beta is the inverse temperature and v is the volume of the system, times the pressure of the single real scalar field evaluated with a funny mass term minus sigma tilde squared over 8 lambda. That means that the pressure for the ON vector model is just given as n times the pressure of the free scalar field and a correction term where we have this funny mass term in here. It should be stressed that this is an exact result for a quantum field theory of the ON vector model in the large n limit. And it depends on the coupling explicitly through the appearance of lambda, as well as implicitly through the fact that sigma tilde is in fact a solution to equation. It's the solution to the saddle point condition that's just given or reproduced in this equation 26.22 here. Since the pressure of a free scalar field in 3 + 1 dimensions is divergent, we still need to discuss how to non-perturbatively renormalize this result in the following lecture. And after that, we still want to discuss how the solution to this pressure and also renormalization looks in terms of actual physical quantities, and we'll discuss that also in the next lectures. And this concludes the present lecture.